Good evening, students. Tonight's lesson is going to be over uniform circular motion and also the universal gravitational force. Both topics can be found in the application of Newton's laws module. These are the last two topics of this module. I have covered the other topics in previous help sessions. So let's go ahead and jump right into it. The first thing we need to talk about is circular motion. So remember that uniform circular motion occurs when an object travels at a constant speed around a circular pathway. A force must act on the object perpendicular to the path of the object, so it only changes direction and not its speed. Both force and acceleration point to the center of the circular pathway. Many students forget that the centripetal force is actually pointing to the inside of the circle, because when you are spinning around in a circle or riding one of those rides at the fair, you feel yourself being pushed towards the outside of the circle. So sometimes students think that the centripetal force is pulling them out of the circle, which really the way the physics works is that this centripetal force is actually bringing you towards the force. What you're feeling being pushed against you is the inertia of that motion. Remember, velocity is going to be at any given point will be a tangent to the arm of the pathway, and this is going to be important when we look at an example problem asking specifically to calculate different components at the top of a circle, the bottom of a circle, and on either side of a circular pathway. So let's talk about some of the equations. So first, you must use centripetal acceleration, which is always directed towards the center of the path or perpendicular to the velocity, which is meaning the same thing. So that's what we were just talking about on the previous slides. So specifically, we have the acceleration, which is the centripetal acceleration, can be equal to the velocity squared divided by r, and that r is going to be the radius of that circular path of the object. Again, remember that the velocity, which will be the magnitude of the tangential velocity, which is just what I showed you on that previous slide. So if you look at the picture over here on the right-hand side, you can see that the centripetal acceleration is pulling you towards the inside of the circle, and at any given moment on this circular path, that velocity will be the magnitude of that tangential velocity, which will be exactly perpendicular to that acceleration force towards the inside of that circle. So force is called the centripetal force, and basically using the second law of Newton's, we can find that this equation for centripetal force. So the centripetal force equals the mass times velocity squared divided by the radius. So remember, it is the sum of the forces along the axis which is directed towards the center of that circular path. You should not draw an FBD or free body diagram for these types of problems. And remember that the towards the center is always positive. So just keep in mind also that for our class purposes, we always assume that the object in motion is at a constant velocity. So here is our first example. It states a 2.00 kilogram ball is tied to a 5-meter long string that can apply a maximum tension of 250 newtons. The question asks, how fast can it go in a vertical loop? So we're going to look at 3 different scenarios: at the top of the loop, at the bottom of the loop, and halfway up on either side of the loop. So how we do this is we have to make sure we rewrite our formulas that we have kind of covered in the previous slides. So we have that centripetal force equals mass times velocity squared divided by r. So if we think about the force being the tension plus the weight, or the gravity, you can replace the centripetal force with that equation. Rewrite that equation to solve for velocity. So you can see on that fourth step, we have the velocity equals the square root of the tension plus the mass times gravity, which is the weight. We should know that from previous modules. So the sum of that divided by, or multiply the radius and then divided by the mass overall. So we should get, if you add those from the problem, so we have that 250 newtons plus 2, the 9.8, remember, is the gravity constant. The 2 is the 2 kilogram, that's the mass of the ball, divided by, or the 5, which is going to be the radius, which is also given to us in the problem as how long the string is, because that's going to be where you're holding, or whatever is holding the string to the end of the ball on the circular path. And that should give us 26.0 meters per second. We can do that for the same for the bottom of the loop, and so the difference is here we have oh, I'm sorry. I was thinking that was the side of the loop, so I thought I made a mistake. So again, the top of the loop, look at the difference in the equation. So we have the tension plus the weight because of the mass and the gravity at the top of the loop compared to the bottom of the loop. The tension minus the weight or the mass, so that's going to be mass times gravity. So notice the difference in the equations here. We have the plus sign and then the minus sign. So that's why you're going to have a different result of 24.0 meters per second at the bottom of the loop. Now compared to halfway on either side, we're not going to incorporate the gravity at all, so we're just going to be looking at the radius. So look at the formula for the either side of the loop. So it's going to be velocity equals the square root of the tension of the radius divided by the mass. And if we add those numbers into the equation and solve for it, we should get 25.0 meters per second. Here's the second example. It says a car with a mass of 1,850 kilograms goes around a curve that has a radius of 50.0 meters. The first part of this question is going to ask, what is the force of friction acting on the car if the coefficient of friction is 0.300? So now we're going to incorporate friction into this centrifugal force and motion example. Think about the formulas that you need. We have the force, which is found in newtons, minus the weight equals 0. Remember, the weight equals mass times gravity. So if we plug in what we know, we have the mass of the car, which is 1,850 kilograms, times gravity, 9.8. So we're going to get 18,100. Then we're going to plug in what we know from the coefficient of friction, which is 0.3 times that 18,100, and we should get 5,430 newtons. A lot of students forget to convert the kilograms into that newtons, so make sure you don't forget to do that on the quiz or the test. Problem, or the second part of this problem, which is letter B, says what is the maximum velocity the car can go around the curve? So now we're looking at the velocity, which remember is tangential to the centrifugal force or perpendicular to that pool of the inside of the circle. So if we look at the formula, we have the centrifugal force equals mass velocity squared divided by radius. We have the friction force now, and so now since we've solved it from the previous problem, we're going to plug in what we know from part A, which is 5,430 newtons. Multiply that by the radius of the circle, which is 50, and divide that all by the mass, which is 1,850. And if you plug that into the calculator, you should get 12.1 meters per second. Now we're moving into the last topic of that application of Newton's Law module, and that is called Newton's Law of Universal Gravitation. So the universal of gravitation, remember, it basically means that there is an attractional force between two objects that have mass. This means that they are directed towards one another or attracted to one another. So basically the law states that the force between masses is directly proportional to their masses, and the force between the masses is inversely proportional to the square of the distance between the masses. In other words, if you double the distance, the force is going to decrease by 1/4 of its previous value. You should have seen this relationship in the virtual lab for the gravitational constant. If you did not find this relationship, you need to go back and reassess your values in that conclusion part. To convert the equation to an equality, you must use the universal gravitational constant, which is represented by the letter G. So G is going to be 6.67 times 10 to the negative 11th, and that is the unit. I know that there are some questions about that virtual lab on what is the gravitational constant unit. The nm squared divided by kg squared will be the units for that gravitational constant. The gravitational force equals the gravitational constant, mass of object 1 times mass of object 2 divided by the radius squared, which is going to be the distance. So remember that if we are on Earth, then we will use Earth's radius for r. So make sure you have that number for Earth's radius written down, which is 6.371 times 10 meters. The force of gravity is the same thing as the weight if you calculate the force between an object and the Earth. So here's a practice problem. It says a cosmonaut is a geosynchronous orbit around the Earth. The orbit is 35,786 kilometers above the Earth's surface. The cosmonaut has a mass of 65.0 kilograms. The Earth has a radius of 6,378 kilometers and the mass of 5.9723 times 10 to the 24th kilograms. What is the radius of the cosmonaut's orbit? So we're going to add what we know from the problem, 6,378 plus 35,786, and that's going to give us 42,164 kilometers. We're going to multiply that by 1,000 meters per kilometer for the conversion factor, and we should get 4.2164 times 10 to the 7th meters. Then it's asking for what is the weight of the cosmonaut at this altitude. And the altitude didn't convert, so we are given to it in the problem above. So we're going to have the force of gravity equals the gravitational constant from the mass of object 1 times the mass of object 2 divided by the radius squared. So the gravitational force, after we add in what we know from the problem, should get us in our calculator 14.6 newtons. So double check on that calculation that you're doing that correctly, especially with that scientific notation. And remember that if you need to review the scientific notation, it is found in the Math of Physics module at the beginning of the semester. Here is practice problem number 2. It states, what is the force of gravity between the Earth and the Sun? So the Sun has a mass of 1.99 times 10 to the 30th kilograms, and the Earth's orbit radius is 149.6 million kilometers. So if you have that written in scientific notation, it would be 1.496 times 10 to the 11th meters. So again, we look at the same equation that we were talking about. We add that gravitational constant, add in the numbers that are given to our problem, divide it by the radius of that orbit around the Sun, and you should get the gravitational force is 3.54 times 10 to the 22nd newtons. And that is it for this module. Please let me know if you have any questions if you're watching this as a recording. Thank you for watching and have a great night.